Hypothesis Testing, Introduction by Dr. Yahya El-Maghazi.
Hello everyone. In this lecture we will introduce to you the concept of hypothesis testing. This is a very important subject that goes under the general subject of inferential statistics. Indeed, it is the other side of the coin of inferential statistics. Recall in the previous chapter, we discussed how to establish a confidence interval on the mean of a population, mu. And we provided you with a number of formula on how to establish that confidence interval in view of some of the information that you know about the population, as well as the sample size that we take. In this session, we will be discussing the hypothesis testing, meaning we will be testing some claims or assumptions made about the population to see if they are true or perhaps they are false, or we don't have enough evidence to prove that they are true. The key common factor in both confidence interval and the hypothesis testing is the population mean. As you can see here, we're trying to estimate the population mean, mu, and here we are making a claim about the population mean being equal some value or not equal this value. Let us first recall some of what we said on the previous subject, the confidence interval subject, very briefly before we move on with the hypothesis test. The key issue was we have a population, large population of so many components, and we were interested in estimating some parameters or the values of some parameters of that population. We could be estimating the average of the population or the mean of the population, mu, or perhaps the standard deviation of the population or other parameters. And it's very important to emphasize the term parameters. As I mentioned repeatedly in this course, when we speak of the population, all measures of the population are called parameters. This is a universal, common, simple. We also mentioned that in order to establish a confidence interval or estimation of the population mean, we simply have to take samples from the population. In practice, we may be taking many samples. And when we discuss samples, we have to be very careful, because we told you that the measures of the samples are called statistics. So it's very important that we distinguish between parameters and statistics. Statistics are measures of a sample, parameters are measures of the population. In practice, we may be taking many samples. And as you can see, every sample will likely to have a different average values, as you can see here. We've learned from the central limit theorem that the overall average of averages, or the average of sample averages, is likely to be equal to the population mean mu. If you take in many samples from the population over time, as many businesses do, then after a while you start to establish a good estimate of the population mean based on the cumulative average of the sample averages. If on the other hand I take those sample averages and try to construct a histogram or a relative frequency distribution out of these averages, what I will get is a normal distribution. This is by virtue of the central limit theorem, especially if sample sizes are large or if we take too many samples. Now, let us for a minute assume that the parent population also have a normal distribution. According to the central limit theorem, regardless the distribution of the parent distribution or the parent population, the sampling distribution will follow a normal pattern, as we can see here. We call this sampling distribution because it's a distribution constructed from the average values. Note that the population distribution is typically constructed, if we can, from the individual values of the population. So that is not a sampling distribution. A sampling distribution has to come from sample statistics. You can have a sampling distribution of mean values. You can have a sampling distribution of standard deviations or variances or any other statistic of samples. So what is the difference between a sampling distribution of this shape and the parent population? Well, we've learned from the central limit theorem that the average of the sampling distribution will be very likely equal to the average or the mean of the population. But if we look at this distribution versus this one here, we will note that this distribution is narrower than the parent population distribution. In fact, if I overlap the parent population distribution, you can see that. You can see that the parent population distribution is wide and the sampling distribution is narrow, and they both share the same mean value, as you can see here. So what is the difference between the two? Well, if the sampling distribution is narrow and the parent population distribution is wide, then the difference is in the variability or the standard deviation of the population. If we look at the population distribution, we can term the standard deviation by sigma suffix x, meaning the standard deviation of all x's in the population, x values. On the other hand, if I look at the sampling distribution, the standard deviation of it can be symbolized by sigma suffix x bar. And I want you to pay attention to this because we discussed that previously in or under the subject of confidence interval. Sigma suffix x bar is the standard deviation of averages. And we mentioned that that standard deviation of averages is equal to the standard deviation of individuals divided by the square root of n, and we also called it the standard error. So the standard deviation of averages is universally called the standard error. And as you can see here, it is determined by the variability in the parent population, sigma x, and the sample size. One can easily note that the larger the sample size, the smaller the standard error. So if you want a reduced standard error, then you need a larger sample. This is very important because the standard error is a basic component of the margin of error, as I will discuss next. So we have a population. We're trying to establish a confidence interval on the mean of the population. And as a result, we are going to take a sample from this population. Now, if we take a good sample from the population, and assuming that the sample is fully representative of the population, then we can simply see that this sample will have a frequency distribution or a distribution that is within the population distribution. So we can use the sample average to estimate the population mean. That is what we call a point estimate. Indeed, the average of a sample is an unbiased estimate of the population mean, as we discussed in the previous session. The problem is, if I take another sample, more than likely I'm going to get another mean value. And if I keep repeating that, I'm going to get different averages, some of which will be around the mean, and the other will be way out. In fact, some of them may not represent the population distribution due to some error or by chance. So as a result, we need to add one more criteria of the point estimate, which is what we called the interval estimate. And the interval estimate is equal to a range. So instead of saying mu equal x bar, which is the point estimate, now we're going to say mu is x bar plus or minus some value e, which we called it the standard, the margin of error. So now we have a point estimate and we have an interval estimate. Now we are about to say that not only the mean of the population equal some value, say 30,000 or 50,000, but it may also range from some low value L to some high value U. So we're going to establish a range or an interval estimate. That is the second step in estimation or in establishing confidence interval. The problem with that is how many samples can we take that will fall within that interval from L to U? And what is the chance that some of the samples will be outside that range? So we need some kind of confidence. We need a confidence level. As you recall, we use the 95% or the 99% or the 90% confidence. And they all mean that we are establishing a confidence interval within a certain confidence level or associated with a level of confidence. So when we say we have a confidence of 95%, we are essentially saying that our estimation is very likely to be true in 95% of the time. So if we take 100 samples, 95 of these samples will likely to be or exhibit values within the range or the interval estimate of the population mean. We also explained to you the value of E, the margin of error. And as we mentioned previously, the selection of E will depend on the conditions we have. If we have a population with a standard deviation that is known in advance, if you have the luxury to know the standard deviation of a population, or if the sample size is very large, and we know what's the threshold of sample size being equal or greater than 30, in this case, we can use this term here to express the margin of error. This is the Z score or the Z statistic that we are familiar with times the standard error. And notice here the standard error is determined by the standard deviation of the population. If we know the standard deviation of the population divided by the square root of the sample size. So it's really Z times the standard error. Now, in some cases, people can use this term here or this product here, even if sigma is unknown. This is the case where you have a very large sample. So where are you going to get sigma from? Well, you're going to use the standard deviation of the sample instead of sigma, and your estimation or your confidence interval will still be valid. Now, if we don't know the standard deviation population, we can use this term here, T times the standard error. And we described for you the T statistic. And we told you that's derived from the so-called T distribution, which is a sampling distribution of averages for small samples. We can use that if sigma is unknown, and whether n is large or n is small, we still can use it. The only difference is if n is large, we can use it comfortably, and if n is small, we can use it assuming that the population is normally distributed. All of these are concepts that we discussed previously under the title of establishment of confidence interval on the mean of the population. This was the first side of the coin of inferential statistics. Now we are moving to the other side of the coin, hypothesis testing. In today's session, we will be hopefully completing the following subjects. We'll be talking about what is hypothesis testing, then the key practical steps of performing hypothesis testing, then we will specifically talk about hypothesis testing about population mean, mu, for large samples or when population standard deviation, sigma, is known. And in the midst of doing so, we will be talking about the critical region method and the p-value method. What is the meaning of the word hypothesis? Well, looking at any dictionary, you'll find that there are many words that describe the word hypothesis. It can be described as theory, proposition, supposition, premise, suggestion, guesstimate, assumption. All of these are different meanings of the term or the word hypothesis. Indeed, we live in a world of hypothesis. In just about everything we do, we make assumptions of things to be true, which may turn out to be true or false. A hypothesis test is a claim or a statement about a variable of a population that we would like to evaluate or test. It is important to know the key terms associated with hypothesis. And the first term is a null hypothesis, H suffix 0. Null hypothesis. What does that mean? Null may be taken as none or 0. In statistics, null hypothesis or null means what is known, what is assumed, or what is claimed. Null means nothing new, nothing different, or take my word for it, a claim. So that is a null hypothesis. And it's very important that we understand that our null hypothesis would be about the population of interest. We look at the sticker or the can of soda and we see that 12 ounce is the weight posted on the can. What does that mean? It means that the company claims or specify the weight of the can as being 12 ounce. We take the can of soda and we assume that it's going to be 12 ounce. So that is an assumption. That's the sticker weight. That's specifications. An alternative hypothesis, sometimes called the research hypothesis, would obviously be that mu, or the weight of the soda can, is none. 12 ounce. Here we are not talking about one soda can, we're talking about the population. Can the factory producing or the company producing the soda cans assure us that all cans produced by the company indeed have a weight of 12 ounce? After all, that is what we assume when we drink soda out of a can. Notice that the null hypothesis and the alternative hypothesis are mathematical opposites. So they really represent what we call mutually exclusive outcomes. If the null hypothesis mu equal 12 is untrue, then the alternative will be the true situation, and the other way around. So H0 and HA are mathematical opposites, but they both target the same issue or the same variable: the weight of the can, the student's grade, the income, or whatever the variable that we are dealing with. So it is important to understand that we will have a null hypothesis, and we will also have associated with it an alternative hypothesis. Now, is mu equal versus mu not equal are the only format of hypothesis testing? Obviously not. Why? Because the alternative hypothesis can take other format. Meaning, is the only alternative to mu being equal 12 is mu not equal 12, or there are other alternatives? Think for a second. Obviously, if the null hypothesis is mu equal 12, the alternative can either be mu not equal 12, or mu greater than 12, or mu less than 12. So for each null hypothesis, there are basically three possible alternative hypotheses that we can test. And in this chapter, we will test all of these hypotheses. The outcome of a hypothesis test is typically we can either reject the null hypothesis or we fail to reject the null hypothesis. We can reject that the can of soda has a weight of 12, or we fail to reject that the can of soda has a weight of 12. Notice the focus here is on the null hypothesis. We did not mention anything about the alternative hypothesis. Only when we reject the null hypothesis that we can proceed to the alternative hypothesis. It's also important to know that we never say accept, meaning if we reject the null hypothesis H0, that does not mean that we are saying we accept the alternative hypothesis. So failing to reject does not mean acceptance. Failing to reject the null hypothesis does not mean acceptance of the null hypothesis. When we fail to reject the null hypothesis, that doesn't mean that we are accepting the null hypothesis. Accept is not a statistical term. Indeed, all what we're saying is that the data support the alternative hypothesis in case we reject the null hypothesis, or we are saying that the data does not support a rejection of the null hypothesis when we fail to reject the null hypothesis. So it is based on what we have. Does the data support the rejection, so we reject, or the data does not support the rejection, so we fail to reject? Statisticians never use terms such as certain or absolute or accept. Instead, statisticians typically use terms such as possible, probable, fail to reject, indicate, support, or unsupported statement. So now we have reached the point where we know that the hypothesis test has to be formatted in terms of null hypothesis and alternative hypothesis. And this is the beginning of any hypothesis testing. And we also seen the end of any hypothesis testing, which is the outcome of a hypothesis testing, which is either to reject the null hypothesis, H0, or we fail to reject the null hypothesis, H0. Did we learn how to test a null hypothesis already in previous sessions? The answer is yes. We learned that in the confidence interval discussion. Indeed, in the confidence interval, we took a sample from the population and we tested the sample and we calculated the descriptive statistics of the sample, the average and the standard deviation. And at the end, we were able to establish a confidence interval of mu. Here, for example, if x bar is equal to 12.2, standard deviation is 0.2, and the sample size of 36, the confidence interval will be mu from 12.13 to 12.27. Notice in this range, we don't see 12. What is 12? Well, 12 is the null hypothesis. So if 12 does not exist in that range, that means we should automatically reject the null hypothesis. Now, if I take another sample, same size, and I found out that the average is 12.1 and the standard deviation is 0.4, then in this case, I'm going to have a different confidence interval. Here, as you can see, it's 11.97 to 12.23. What does that mean? It means it's a range that the value of 12 lies in it. So in this case, we will fail to reject the null hypothesis. The point of this slide is that test of hypothesis is achieved almost fully using the confidence interval. The problem with that is that we need to go and focus more on the hypothesized value, on the 12. We need to understand what is the chance of samples meeting this null hypothesis or not meeting these values. And that's the probability aspect of hypothesis testing that I will discuss shortly. There are a number of basic steps of hypothesis testing. The first step is to identify and define the characteristic under consideration and state the null and alternative hypothesis about the value of the characteristic in the population. It is very important that we do that, because if we don't have a hypothesis test format, then we don't know what we're testing. We need to be able to establish this first. The second step is we take a representative sample from the population of interest, we test it, collect data, and determine descriptive statistics. And yes, for the purpose of what we're doing here, we need the average of the sample and the standard deviation, and of course, the sample size. The third step, we need to establish some sort of confidence or significance or risk associated with our decisions. And that is what we call type 1 error. The next step, we need to identify and calculate an appropriate test statistics. And the final step, we need to make a decision following some criteria that I will explain very shortly. Let's take these steps one by one. The first step is to identify and define the characteristics under consideration and state the null and alternative hypothesis about the value of the characteristic in the population. How establish this? Is it mu equal versus mu not equal? Is it mu equal greater than versus mu greater than mu zero? Or is it mu equal versus mu less than mu zero? We have to understand how to establish a hypothesis test format. Well, the way we decide on the appropriate format of hypothesis is dependent on the status quo or the claim. For example, if we say a chocolate bar has a 5 weight on the sticker, chocolate bar has a 5 ounce or 5 gram weight. The obvious hypothesis in this case would be that the null hypothesis mu equal 5 gram and the alternative mu will be not 5 gram. So H0 will be mu equal 5 and HA will be mu not equal 5. It has to be exact. If the chocolate bar is greater than 5, that means the factory producing the chocolate bar is losing money. Yes, we will be happy if we get more for our money, but the company will not. On the other hand, if the chocolate bar is less than 5 gram, we will not be happy. We will be dissatisfied, and the company has to do something about it. So that is one of those variables that has to be exact. Another way is the claim. Suppose that a company claims that the delay of time to respond to customer calls does not exceed 10 minutes. Now here we have to be very careful. The company is claiming that their customer support reply or response to customer calls does not exceed 10 minutes. And by saying that, they actually mean that the time is either equal to 10 minutes or less. So that's obviously the null hypothesis that we are trying to test. And the alternative in this case will be mu greater than 10 minutes. How about this example? The fuel efficiency of a car is greater than 35 miles per gallon. And I apologize for spelling fuel wrong. In this case, the null hypothesis will obviously, based on the claim that the fuel efficiency is greater than, we're going to put it as is. It's greater than or equal 35 miles per gallon. And the alternative that we need to test would be that mu is less than 35 miles per gallon. This is a key issue. Now, if we don't have any one of these situations, in other words, if we have to develop our own hypothesis testing format, like in a research or a study or a term paper, in this case, we really have to think of the different categories of variables. If you recall, early on in this course, I divided variable to you into three main categories. Nominal, the best variables. Those are the variables that have to be exact, typically dimensional characteristics, weight, length, thickness, area, and the volume. Then larger, the better. These are the variables that are better when they are large: income, profit, health, performance parameters. And then smaller, the better variables. And those are the variables that are preferred to have small values. The number of accidents on a job, the number of students with math anxiety, the number of homeless people, and so on. The point here is you really have to understand the nature of the variable in order to establish a good hypothesis testing format. Now let's go to the next step. But before I do that, I need to point out that if the null hypothesis is equal versus not equal, we will call this a two-sided test of hypothesis. And just to keep in mind, for the time being, that two-sided refers to the normal distribution. Here are two-sided values, meaning our confidence will be in the middle, and we're going to have a risk taken that will be divided equally into two parts, one in the right and one in the left. If we are talking about a one-sided test, which is the one that involves greater than or less than, then we will be talking about only one side of confidence or one side of risk. So the idea here is, depending on the test, we're going to decide on the risk we will take. For two-sided test, the risk is going to be divided equally into two equal parts. For one-sided, the risk will be taken completely and entirely on one side. For right now, you also need to note that when the alternative is greater than, we go to the right side of the distribution, and if the alternative is less than, then we go to the left side of the distribution. We will explain that very shortly. Step 2, as I said, we take a sample and we calculate the descriptive statistics of it. And of course, we covered that a great deal in previous chapters. We discussed with you how to select a representative sample and how a sample representation should be done in a very accurate way. A representative sample is typically a sample taken from a population such that each component in this population has the exact same chance of being selected in the sample. That's what we call it, a fair and representative sample. So I'm not going to talk much about this because we discussed it before. It's very important, as we take the sample, that we test the sample, we collect data, and we calculate the descriptive statistics. And the important statistics with respect to our subject is the average of the sample, the standard deviation of the sample, and of course the sample size. Just like we did with the soda cans in the previous example. You could perform a confidence interval at this point to use it later on to verify the test result, or that could be the end of your testing of the hypothesis if you chose to do so, but I would not recommend that. The next step is the type 1 error. Type 1 error is what we call it the level of significance or risk. Is how confident do we want to be in making the decision about the hypothesis test, or how much risk we're willing to take in making the decision about hypothesis test. Does our conclusion in hypothesis testing matches the actual state of reality? Could we be committing some kind of error? How confident are we in our decision to reject or fail to reject? All of these are key questions that stems from this step, which is the selection of type 1 error. And you can see now that type 1 error will have a lot to do with the confidence interval that we mentioned in the previous chapter. Indeed, if you go to the previous chapter in establishing confidence interval and you say that I established a confidence interval with 95%, then type 1 error will be 1 or 100 minus 95% or 5%, and in case of two-sided test, that 5% will be divided equally, as you can see here, on both sides of the normal distribution. In selecting the type 1 error, we have to understand the meaning of type 1 error. Typically speaking, when we make a decision about a null hypothesis, we have to make that decision with understanding that there is also a reality, meaning the null hypothesis could be true or could be false. So, and that's reality. If our decision is to reject the null hypothesis and the actual value turned to be false, then we have made the correct decision. If on the other hand, we have rejected the null hypothesis while the actual value is true, then we have committed type 1 error. So what is type 1 error? Type 1 error is the chance or the risk of rejecting a null hypothesis while it is true. Can this happen? Of course. Indeed, since we rely on a sample, if that sample is not selected appropriately, then we could easily commit type 1 error. The good news is it's a risk we are willing to take, and we also account for it in our analysis of hypothesis testing. On the other hand, suppose we do not reject the null hypothesis. Well, if we do not reject it and it turned out to be true, then we have made the correct decision. But if we do not reject it while it was indeed false, then we have committed what we call type 2 error. So type 2 error is the chance or the risk of not rejecting a null hypothesis while it is false. So in summary, type 1 error occurs if the null hypothesis H0 is rejected when it's true. This type of error may result in taking actions that are not necessary, what we call it over-controlled thinking, or it may result in unnecessary modification of a process. Type 2 error, on the other hand, if the null hypothesis H0 is not rejected when it is false, then a type 2 error has occurred. This may lead to an opposite action to that of type 1 error or under control. It's also important to know the mathematical expressions associated with type 1 error and type 2 error. Alpha or type 1 error is the probability of committing type 1 error. It is a conditional probability, as you can see in this term or in this expression. It is the probability of rejecting a null hypothesis given that the null hypothesis is true. Beta is a universal symbol of type 2 error, or the probability of committing type 2 error, and it's equal to another conditional probability, which is the probability of failing to reject the null hypothesis H0, given that H0 is false. It's also important to know that type 1 error is equivalent to the risk alpha you take in estimation. So type 1 error as a term is not a strange term to all of us. We have used it in establishing confidence interval. It was the complementary probability of the confidence level. We can easily visualize type 1 error and type 2 error as follows. Suppose we have this example here. Mu equal 12 is the null hypothesis. Mu not equal 12 is the alternative hypothesis. Keep in mind that mu is the actual mean of the population, and the mu 0 or 12 is the hypothesized mean of the population. So they both are talking about population here. So if we take a sample from the population, such as the soda cans in the example of soda can weight, and established some form of confidence interval, we will see that one sample may have an average, say, of 12.2. That's the sample that we ended up rejecting. Another sample may have an average of 12.1. That's the one that we failed to reject because it was associated with a confidence interval covering the mean of the population or the claimed mean. And if we keep doing that, we're going to see some samples that are in and some samples that are out. But as you can see in this example here, most of the samples that we take were within the acceptance value of mu equal 12. And what does that mean? It means this sample here was an odd sample. This is the only sample that we ended up rejecting. So by taking this sample, if this is the only sample that we use in our analysis, we have indeed committed type 1 error. Because using this particular sample, we ended up rejecting the null hypothesis of mu equal 12 while it's actually true. Now, how do we know it's true? We know that if we keep taking many samples and see that most of these samples fall within the range. That's just a practical visualization of how type 1 error is committed. When we say a 5% type 1 error, we are in essence are saying that if we repeat sampling 100 times, then 5 times, that is if we talk about 5% type 1 error, of the samples are likely to fall outside the claimed value. In other words, 5 samples are likely to be associated with type 1 error. Type 2 error is the opposite of what I just said. Suppose we take in many samples and we keep rejecting the null hypothesis based on the fact that these samples are outside the range. Indeed, the actual mean would be somewhere in the middle of these samples, right here. Now, if we happen to take a sample like this one here, and it happened to be within the range, meaning we're going to fail to reject it, that is an indication of committing type 2 error. Why? Because if this is the only sample we have, we will end up making a decision of failing to reject, while indeed the average mu of 12 should not be the true average. It is false. And again, if we talk sample and it was by chance like xi bar, we would incorrectly fail to reject the null hypothesis while it is false. This is the type 2 error, or the probability of fail to reject the null hypothesis when it is false. This slide, I mentioned it early in previous sessions about some values that we will use often, the z values. We use these values at 99% and 95% and 90% for establishing confidence interval, and most of these values have become household. When we say 99%, we know that z is 2.58, 95% we know that z is 196, and 90% we know that z is 1.64. Also, if we have a one-side test, as we will do shortly, then at 99% the z will be 2.33, at 95% the z will be 164, and at 90% the z will be 1.28. Now we move to identifying an appropriate test statistics. Well, the appropriate test statistic follow the conditions that we mentioned in establishing confidence interval. If we have a population with a known standard deviation or very large sample, and assuming normality if it's a small sample with known population, we will use the z, and if we have a population of unknown standard deviation, we'll use the t. Now, what t? These are not the critical t or the critical z. These are the so-called test statistics. If you look at this formula here, this is a simple definition of the z-score. Remember the first time I introduced the z-score, it was x minus mu divided by sigma. The only difference this time is that we're no longer talking about individual values, we're talking about average values that we're going to use in testing the hypothesis. And the x bar, or the average value, would be subtracted from the claimed mu, that's assuming the null hypothesis is true, divided by the standard error, sigma of the averages. Same thing with the t, and you can see the similarity of the two formulas. The t0 or the test statistic is x bar minus mu 0, and since we don't have sigma in this case, we use the standard deviation of the sample divided by the square root of the sample size. Now we move in to the process of criteria of making the decision. When we have a certain risk level, such as 5% or 1% or 10%, in the regions of the risk, like this case, for example, the mu equal versus mu not equal, we will reject the null hypothesis if the test statistic fall in these regions. That's how simple the criteria of rejection is. In the one-sided test, if the test statistic is in the risk region, in this case it would be the right-tailed region, meaning the test statistics is greater than the critical Z, then we will reject. If the test statistics is in this area, we will fail to reject. Similarly, if we are talking about left tail test like this one here, if the test statistic is in the risk area, we reject, and if it is in the confident area, we will fail to reject. Now, notice that the difference between this and the other two is that in the two-sided test, we are distributing the risk into two equal parts. So the alpha would be alpha over 2 here and alpha over 2 here, meaning if I have a 95% confidence, I will have 2.5% here and 2.5% type 1 error. While if I'm doing a one-sided test, the whole risk will be put in one side or the other. Here is the entire alpha. So if this is a 5%, that means the region of no rejection will be a 95% in both cases. Finally, let's take an example following the steps that we mentioned. Step 1, we're going to identify and define the characteristics under consideration and state the null and alternative hypothesis about the value of the characteristic in the population. And the claim is one of the examples we mentioned before, that the delay of time to respond to customer calls does not exceed 10 minutes. What does that mean? It means here is the claim, it does not exceed 10 minutes, means it's equal or less than 10 minutes, and the alternative is going to be greater than 10 minutes. Now, what's the procedure? We take a sample. Suppose we take a sample of a number of calls, say 49 calls, and measure the time, and we found that the average is 10.3 minutes, and the standard deviation of the population of time happened to be 0.8, so we know the standard deviation population. Then in this case, we have to decide first on type 1 error. Suppose we are using a 1% type 1 error. Now, as soon as we decide on type 1 error, we need to sketch the normal distribution, because given the fact that the alternative is greater than, we will automatically go to the right side, and we're going to put the entire error of 1% in this area here, which means that the critical Z will be 2.33, very much like we did in confidence interval, and also means that if the Z statistic which we are about to calculate is in the here or in the rejection region, we will reject the null hypothesis, and if it is here or in the do not reject region, we will fail to reject. Once again, if the Z statistic is here, we will reject. If the Z statistic is here, we will fail to reject. So let's calculate the Z statistic, and we know it's a Z because the standard deviation is given, and the Z, as I mentioned a minute ago, it is equal to X bar, the average of the sample, minus mu 0, the claimed value of 10, and divided by the standard error, which is the standard deviation of the population, divided by the square root of the sample size. Now you see here that the Z statistics is 2.625, which is greater than the critical Z of 2.33, meaning that the Z statistic will be here, meaning we will have to reject the null hypothesis. We will have to reject the claim made by this company that the average time to respond to customer calls does not exceed 10 minutes. That doesn't mean we are 100% sure that the average time exceeds 10 minutes. We're simply saying that based on the sample and the statistics we obtained, these statistics cannot support the claim by this company. As a result, we have to reject the null hypothesis. We can always verify what we did by doing the confidence interval on the mean. And as you can see, if you follow the procedure we discussed in the previous chapter, here is the mean at 99% fall from 10.01 to 10.6. So it's definitely a range that does not include the 10. It's outside the 10 range, which means the rejection of the null hypothesis was indeed justified. Here is another example, the soda can. And I did the confidence interval on the soda can previously when we had a 36 cans, average of 12.1, standard deviation of 0.4. Suppose we select the type 1 error of 5%. Here we're talking about two-sided tests. So we divided the risk into two equal parts, as you can see here. And that means each part will be 2.5% or 0.025. And the middle area will be the 95%. And of course, the Z statistic here is calculated by the average minus mu0 divided by the standard deviation divided by square root of sample size. Here we don't have the standard deviation of the population, but the sample is large enough to use the standard deviation of the sample. So it's okay to do that. 12.1 minus 12 divided by 0.4 over the square root of 36 is 1.5, which means if we position the 1.5 into this graph, we will find it to be inside the range or in the no rejection region. Remember, the critical value at 95% is 1.96. So only outside the 1.96 to the right or the left will lead to a rejection. So since the Z statistics fall between these two lines, it is in the no rejection region, and we can actually decide to not reject or fail to reject the null hypothesis of mu equal 12, and we can also verify that by establishing the confidence interval. And as you can see here, the 12 for sure comes between these two values. So 12 is within the range, which verifies our decision. The next method to make decisions is the so-called the p-value or the probability method. It's very simple. If we take the same example we talked a minute ago, we can go through all the steps up to the point where we calculate the Z statistic. Now, remember, we have the critical value of 2.33, and we have the Z statistics of 2.625. The p-value or the probability or the area value is based on finding the probability or the area associated with the test statistic. So if I put the test statistic here, and I am in the one-sided test, meaning I'm looking at this area here, then I will have to find the probability associated with the test statistic or this area here. Now, I can go to the Z table or the normal table and find the area. And as you can see here, our area is 0.0043. Now, note that this area is much smaller than the rejection area of the 0.01. This area here at 99% is 1%. So if the probability obtained, if the probability associated with the test statistic is smaller than the type 1 error, then we are to reject the null hypothesis. There is a great deal of discussion that can be made about the significance of the p-value or the probability value. But at this point, what I would like you to remember is that when we say that the p-value is 0.0043, this is simply the chance or the probability of having samples that are more extreme than this sample, meaning samples that are in this side, which support more our rejection decision.